Right. Hi, guys. Welcome online. Good afternoon to all of you. Now, before I begin, I just want to do a sound check. So, if you cannot hear me clearly, please indicate using the raise hand gesture. Okay, I think some of you cannot hear me clearly. Let me adjust my mic first. Hello, is it okay now?
Yes.
Okay, great. I think most of you are already online. We are expecting 90 plus people. So I think we are reaching that number. Okay, so let me get started. Now, before I begin the lecture for today, I just want to do an overview of part 2. Now, as you know, part 1 has concluded. So from today onwards, we are going to begin part 2 of this H3 course on semiconductor physics and devices. So I'm not sure whether all of you have met me before. I think I met some of you during the lab classes, and of course, I'm your tutor for the tutorial groups 2 and 4. Right, so I think I've met quite a number of you, but in case you haven't met me before, so I just do a self introduction, a brief one. So that's my name, right? My surname is underlined, A-N-G Ang. Right, I'm with the School of EEE NTU, the same school as Prof. Ng. All right. Now, what you see here is my email address. So you can note that down. But anyway, it's on the slide, and you already have a copy of the slide, I believe. So the purpose of giving you my email address is to allow you to send me your queries, your doubts, your questions about this course anytime you wish. All right, I'll try my best to answer your questions as soon as possible. Usually within a day. If not, it will be 2 days after you send the email. Okay. Now, if you need to see me, right, which is not quite likely because NTU, as I know, is very far away. Right. But any case, I've included my office address here. So it's S2.2 B2-21. All right. For those of you who have come to NTU before, you know it's quite a maze. So I'm not sure if you can successfully locate my office. Anyway, it's here. The address is here. And my office telephone number is also shown here. All right, in case you have any urgent matter that you need to talk to me. All right, so feel free to give me a call. Okay, so this is just a very brief self-introduction. So I'll be with you from lecture 8 to lecture 14. Okay, so essentially all the way to the end of this course. Now, before I start the lecture, I just want to do an overview of part 2, just to give you an idea what you'll be learning in this second half of the course. Now, there are 3 important topics that I'll be covering, as shown here. All right, so what we are going to do today is PN junction. PN junction has a more common name called the diode. And I think some of you know what a diode is. And in fact, I think in lab 1, you have used a light emitting diode in your experiment. Okay, so you'll be wondering why the diode can give out light when voltage is applied across it. However, if you reverse the voltage, you'll see that the light is not coming out at all. All right, so the diode has quite a fascinating behavior. So we are going to cover the physics behind this behavior. Now, after that, we are going to look at another diode, which essentially is made out of a metal and a semiconductor. Okay, now the PN junction diode that we are going to cover first is entirely made up of a semiconductor. All right, so it is also interesting to know that you can also have a diode, all right, form if you put a metal on a semiconductor. Now this is quite unusual because all of us know that metal is a resistor. It has very low resistance, in fact, and semiconductor by its own is also a resistor. So if you connect two resistors together, the net outcome should still be a resistor. All right, but for certain kinds of metal and certain kinds of semiconductors, essentially N-type or P-type, we might end up with a diode. Okay, right? So it is quite interesting to know why this can be the case. And in the third topic that we're going to cover, right, we will focus on the applications of the PN junction diode by looking at two major applications. The first one is LED, light emitting diode, which you have used before in your lab 1. Now, the second application that we're going to look at is a photodetector. All right, the photodetector basically operates in an opposite manner compared to the LED. Right, and a photodetector is actually very commonly used. In case you do not know, you have been carrying millions of these photodetectors with you every day, essentially on your phone, on the camera of your phone. Okay, so we are going to see how it actually works, how it allows you to take a picture. Right, so these are the three major topics that we are going to cover for part 2. Okay, the next thing I want to tell you is the textbook. Probably Prof. Ng has already mentioned this to you earlier. So part 2 will essentially look at these few chapters, right, which covers the PN junction and as well as the metal semiconductor junction. Okay, so you're encouraged to read the book for more details, and also you're strongly encouraged to try out the questions found at the back of each chapter in the book. Okay, so you can have more practice beyond the tutorial questions if you do that. All right, so that's the textbook, and I think that's about all I want to tell you. Is a very short overview. Now, before I begin, I just want to ask at this point whether there is any question. All right, if you do not have any questions, then I will start the topic on PN junction diode. I'm going to begin with a brief introduction. The idea is to introduce to you the unique electrical behavior of a diode, which is quite different from that of a resistor. You might be already very familiar with a resistor, and you know that the current voltage relationship of a resistor follows the Ohm's law. Right, in other words, V and I, the voltage and the current respectively, are linearly related, and the ratio of V over I is the resistance. Okay, and a resistor allows current to flow easily in both directions. All right, and in fact, if you just reverse the polarity of the voltage applied across the resistor, the same the same current will flow, but in the opposite direction. However, this is not the case of a diode or the PN junction. It has a rather unique behavior shown here. If you plot I versus V, you will get a graph that looks like this. All right, now the circuit symbol of a diode is made out of a rectangle with a line at the vertex of the rectangle here. Okay, so one terminal is called the anode, and the other terminal where the vertical line is called the cathode. So the anode is a positive terminal and the cathode is the negative terminal. So essentially, if I apply a voltage in this manner where I connect the positive voltage of the battery to the anode and the negative terminal to the cathode, I only need a very small voltage to cause a large flow of current through the diode, as shown on the graph, right? After some small voltage, you can see that the diode current rises very significantly. All right, so this behavior is known as the turning on of the diode. So the diode turns on and allow a huge current to flow through it. Now, on the other hand, if we reverse the polarity of the battery, in other words, now you connect the negative terminal to the anode and the positive terminal of the battery to the cathode, or in other words, V is a negative quantity, all right, you will notice that very little current can flow through the diode, hardly any current, very small current, typically on the order of 1 picoampere or 1 nanoampere, in that range, okay? Now, if you keep increasing the magnitude of the voltage that you apply, when it gets large enough, essentially a large current can also flow through the diode. But this voltage at which a large current flows through a diode is much larger than the positive case, right? The voltage here at which a large current can flow typically is on the order of tens of volts or even hundreds or thousands of volts. Okay. On the other hand, a small positive voltage is just enough to turn on the diode, and this voltage is actually less than 1 volt. Okay, so there is a huge asymmetry in the IV relationship of the diode shown here. And we call the diode a rectifying device in the sense that it allows current to flow easily in one direction, but it blocks the flow of current in the reverse direction. Okay, so what we want to do here is to understand the physics that control such a behavior. Okay. Now, before I touch on the physics, I just want to tell you some common applications of the PN junction diode. I've listed some down here, but this is just a small fraction of it. Right? There are many applications that you can find for the PN junction diode. So I will just run through some examples here, like the rectifier circuit, the electronic switch, variable capacitor. Variable capacitor, I don't think I have a slide on that. We might be able to better appreciate how a PN junction diode can function as a variable capacitor later on after we cover the chapter on capacitance. Okay. Diodes are also used in input-output protection circuitry of microchips. And in fact, nowadays, they are used in TV, right? I'm sure you probably have an LED TV at home nowadays, right? So on the screen of the TV, essentially, you have many small LEDs, right? Millions of them. Solar cell, right? A PN junction diode can also function as a solar cell, converting sunlight into electricity, right? So it's interesting to know how that can happen. And the PN junction diode is also an important part of other semiconductor devices, an example of which is the bipolar junction transistor. If you recall, in lab 1, you have used this in your circuit as a switch to control the LED light display that you built. Okay, So in the in the bipolar junction transistor, we have actually two diodes. Okay. If we have time, then I can go through how the BJT behave. All right. So let me just briefly touch on some of the more important application. A very important application where you find diode is the bridge rectifier circuit connected up like this. So there are 4 diodes shown here. Okay, now the purpose of such a circuit is to convert the AC voltage into a DC voltage. And it works like this. It's quite straightforward in a sense that, okay, so imagine now the AC voltage is in a positive cycle. Okay, so we are in a positive cycle of the AC voltage. So this point here will become positive, all right, relative to this point, and therefore diode D1 can turn on easily. As you know, earlier I told you that you only need a very small positive voltage to turn on the diode. Okay, so the diode D1 can turn on easily, so that allows a current to flow through the rest of the circuit. And this current will return via D2. Okay, all right, where D2 is also turned on due to the way the voltage appear across the 2 terminals, right? The voltage at this terminal is more positive than the voltage at this terminal. Okay, so that will cause D2 to turn on. All right, so that is during the positive cycle. So the positive cycle of the AC voltage will now appear across the circuit here, shown by the dashed line here. Okay, all right. Now imagine that you are in the negative cycle of the AC voltage. So what happens in the negative cycle? All right, so this point in the circuit will have a very negative voltage. All right, so D1 cannot turn on now. Okay, on the other hand, this point of the circuit will be at a positive voltage relative to this point. Okay, so diode D3 will now turn on, right? Allowing current to flow in the same direction in the circuit, and this current will return via D4, which will also turn on. Okay, so the voltage, the AC voltage, which is the negative cycle, the AC voltage now appears as a positive voltage across the load, like this. Okay, so this is how this circuit can convert an AC voltage into a DC voltage waveform, like this. All right, now just to add a little bit more, now there is usually a capacitor connected across the rest of the circuit. Right, the purpose of this capacitor is to smooth out the is to smooth out the DC waveform. Okay, so without the capacitor, the DC voltage waveform that you see across the rest of the circuit will be shown by the dashed line here. Okay, it fluctuates very significantly. Now with a capacitor across here, the capacitor can help you smooth out the fluctuating waveform like this. Essentially, it's quite easy to understand. So let's say we are at the positive cycle of the AC voltage, right? Then the current will flow like this, and it will charge up the capacitor at the same time as drive the rest of the circuit. Okay, right? Now, when the voltage at this point, when the AC voltage starts to fall below the voltage at the capacitor, right, then what happens is that the capacitor will discharge and sustain the current flow in the rest of the circuit. Okay, so the voltage, if the capacitance is large enough, then the voltage fluctuation can be minimized like this. Okay, through the use of a capacitor. All right. Now, why this is important? Because we find such a circuit in the power adapter of your electronic gadgets. Like, for example, the handphone charger, you will find such a circuit, all right, which essentially allows you to directly plug your charger into the AC mains, right, in your house. Okay. Right, so inside the adapter, we have this circuit that basically convert the AC waveform into a DC waveform. And of course, besides this rectifier circuit, we also have a step-down transformer to reduce the voltage from the 240 volts down to the charging voltage, which is typically around 5 to 10 volts. Okay, so this is one important application. Now, the next application is electronic switch. So you can use diode as an electronic switch. This is quite easy to understand based on the way the electrical behavior of the diode is. Okay, essentially it allows current to flow easily in one direction, but not in the other direction. So when you apply a small positive voltage, then the diode will turn on, as though a switch has been turned on. And if you reverse the polarity of the applied voltage, the diode actually turns off. Right? It turns off and it does not allow current to flow. Okay, electronic switch. Now this is related to the microchip. All right. A diode can also be used to protect a microchip from excessively high external voltage. And this is how it works. So we connect two diodes like this. By the way, based on this example, these two diodes are called Schottky diode. You will learn how a Schottky diode operates later on. Essentially, a Schottky diode is made using a metal and a semiconductor, right? But the behavior is exactly the same as the PN junction diode, right? Whereby a small voltage can cause it to turn on, and if you reverse the voltage, it turns off. Okay, so it works like this. So this is an external pin of your microchip. So due to some reason, there might be a very large positive voltage appearing here due to an ESD event. ESD stands for electrostatic discharge. Now, electrostatic discharge event can easily happen if you walk across a carpeted room, for example. You pick up charges and then you will discharge when you touch a metal part, right? So that will send a huge current through the circuit, and this might damage the circuit. So imagine now we have a large positive voltage appearing here. Okay, so what will happen is that, all right, this will cause this diode to turn on and allowing the current to be bypassed. Okay, now as you know, after the diode turns on, the voltage drop across the diode is very small. Okay, so that helps to protect the microchip. Right. Wow. Similarly, when you have a negative voltage appearing here, then this diode will turn on and allowing the current to be bypassed. Right. So that also protects the microchip itself. Okay. Yeah, this is LED. All right. So you have seen this in lab 1. So an LED actually is an electronic component that gives out light when you apply a voltage across it, and it is actually a PN junction. Okay, so later on we'll learn in more detail how a PN junction can emit light when the voltage is applied across it. Okay, now LED is very important nowadays because it is used as lighting in most homes nowadays. Okay. Right. The next important application example is solar cells. Right. So as you know, solar cell converts sunlight into electricity, and in fact, each solar cell is a PN junction diode. So how does light get converted into electricity? Right. So you would be able to understand this quite easily after you have learned the theory behind the PN junction. All right. And last but not least, PN junction diode is found in other semiconductor devices such as the BJT. All right, you have used a bipolar junction transistor in lab 1 as a switch. So after applying appropriate voltages across the BJT, you can see that the BJT can be made to turn on, right? And if you don't apply the correct voltages, then it will turn off. So, well, essentially, a BJT is made out of two PN junctions arranged like this, back to back. Okay. Now, besides being a switch, a BJT can also be used to amplify an electrical signal. Okay, so it would be interesting to try to understand how the amplification happens. Right, if we have time, well, I will touch on that. Let's see how it goes. Because online lectures normally can proceed at a much faster pace than on-site lectures. Okay. All right, now the PN junction diode is also found in another very important transistor called the metal oxide semiconductor field effect transistor. All right, some of you might have heard of this acronym called CMOS, CMOS. Right, this is one part of the CMOS circuit, right, where you can find two diodes, right, on each side here. I won't go into detail how this works. The way this transistor works is quite different from the way the bipolar junction transistor works. Okay, it is not exactly based on the diode, right? It is based on another phenomenon called the field effect. So I'll leave it to you to read up on your own if you are interested to know more how this MOSFET functions. Okay. Yeah, so these are some of the important application examples of a PN junction diode. All right, so well, let me state the specific objectives of this topic. Well, we want to learn the physics behind the operation of the PN junction diode, as that will help us, right, design a diode that can meet certain specification, and as well as serving as a foundation, right, for understanding other more complicated semiconductor devices such as the BJT or the MOSFET, and so on. There are many, many more semiconductor devices. Okay, so in the rest of the discussion for today, we want to answer these two questions, right? We are trying to prepare ourselves to answer these two questions. So why does a diode conduct only in the forward direction? Forward as in the positive voltage is applied to the anode and the negative voltage is applied to the cathode. So people call this the forward direction. Okay. On the other hand, right, the diode does not conduct in the reverse direction. Okay. And eventually it can also conduct if the voltage you apply is large enough. Right. So the discussion will help us understand these two questions. Answer these two questions. Okay. Okay, so that is a very short introduction, right? So I hope you are okay now. Are you okay? Are you still okay? I think there's someone trying to send something to me. Yes, Hong Yi, you have raised your hand? Hong Yi, are you around? Probably it's much earlier, right?
Sorry, Prof. I think it was an accident.
Oh, okay. Okay, then let me start the chapter on electrostatics of the PN junction. Okay, so what do we want to achieve in this chapter? I think you know the meaning behind this word electrostatics, right? In the study on electrostatics, people are concerned about charges, electric field, and voltage or potential. All right. So when I say electrostatics of the PN junction, we are basically focusing on these three things as well. We are focusing on the charges at the PN junction. We are focusing at the electric field at the PN junction and the voltage present at the PN junction. So you might start to wonder, why are there charges present at the PN junction? Why is there electric field or even the voltage present at the PN junction? Right? I thought electric field and voltage are only relevant when you start to apply an external voltage, like connecting a battery across the diode. But even without doing so, without an externally applied voltage, right, there is already a voltage present at the PN junction, an electric field present, and some charges are stored at the PN junction. Okay, so well, let me just describe the basic structure of a PN junction, right? Essentially, it is formed. PN junction is formed when an N-type semiconductor region is brought into close contact with a P-type semiconductor region. Now, this statement itself can be misleading in the sense that you might think that physically, if I bring a P and an N semiconductor together, I get a PN junction. Usually, not the case. The PN junction that you create by doing so is or has a very poor electrical behavior. We do not make a PN junction by physically bringing a P and an N semiconductor and make them contact each other. It's not like this, okay? Later on, I will tell you how an actual PN junction looks like and how it is fabricated. Now, schematically, for the rest of the discussion, we are going to represent the PN junction like this, okay? Usually, we put the P on the left side and the N on the right side, but there's no reason why we cannot reverse the two, okay? Right? Now, there's a term that you need to get used to. This term is called the metallurgical junction, which is shown by the vertical line here. Now, what is a metallurgical junction? A metallurgical junction is the location, right, at which the net doping is 0. Now, this applies to a homojunction. So what is meant by a homojunction? A homojunction is one that is made of the same semiconductor. So you just dope one side of the semiconductor P and dope the other side N. But the semiconductor is the same for both regions. Okay? So for a homojunction, the metallurgical junction refers to the location where the net doping is 0. Okay? Now, a PN junction diode can also be formed using two different semiconductors. All right? And in that case, the metallurgical junction refers to the physical boundary between the two semiconductors. All right? So take note of this name. Now, shown below is the circuit symbol of the diode, which I have already explained just now. So one terminal is called the anode, the other is called the cathode, and there's a vertical line at the cathode to distinguish it from the anode. Okay? Now, there are some basic assumptions that we're going to make to facilitate the discussion and as well as to simplify the mathematics involved. Some of these assumptions sometimes are not valid in the real diode, right? Although the inaccuracy that result from making such assumption is usually not severe. Okay. Now, what we are going to assume for the rest of our discussion is that we are going to assume that the P and N regions are both uniformly doped, right up to the metallurgical junction. So if you see, if you try to plot the doping concentration versus the distance, all right, so on the P side, which is on the left, the doping concentration or the acceptor impurity concentration is constant all the way up to the metallurgical junction. Likewise, on the N side, the donor doping concentration is constant all the way up to the metallurgical junction. So at the metallurgical junction, the doping type changes abruptly from P to N or from N to P. Okay, so it's a step change in the doping profile. And because of this step change in the doping profile, we call this an abrupt or a step junction. All right. Okay. Now, at this point, I just want to caution that an abrupt or step junction does not exist in practice. Okay, it is never possible to create such a doping profile in practice. In practice, what actually happens is that although you can dope the P region relatively uniformly, but essentially the doping concentration will start to change almost linearly. Starting at some point, let's say here, it will start to change linearly from P to N, right? So this behavior is caused by the interdiffusion of the dopant that inevitably happens during the fabrication. Okay, so we never would be able to get an abrupt junction like this. Okay, so in practice, all PN junctions are linearly graded junctions. Okay, due to the fact that the doping profile actually changes almost linearly from one side to the other side. Okay, now, however, the mathematics involved in analyzing a linearly graded junction, are more complex. Okay, so to simplify the mathematical derivations, we are going to just assume an abrupt or step junction. But as I mentioned just now, the inaccuracy that results from such an assumption is not very severe. Okay. Now the next thing I want to caution is that a real PN junction does not look like this. So in case you go away thinking that a real PN junction looks like this, no, it does not. So to prevent this misunderstanding, I added 2 more slides, which I think are not found in the original slide deck sent to you. But anyway, I have posted them onto the course site. You can download them for your reference. All right, so this diagram here shows you a more realistic cross-section of a real PN junction. Okay, so essentially it's a vertical device. All right, a PN junction usually is a vertical device because it is easier to fabricate a vertical PN junction than a horizontal PN junction. Okay, so you have the N and the P region, and you have the insulator. All right. And then on top of the N region, we have a metal making the contact to the N. And at the bottom of the P region, we also have a metal gold making contact to the P region. So the 2 metal contacts allow external voltages to be applied to the PN junction. Okay, right. Now a real PN junction is actually fabricated by this compensation doping technique. Okay, so I think you have heard of compensation doping. Essentially, it allows one doping type to be converted to the other if you add dopant concentration of the other type, right, which is higher than the original type. Okay, so it works like this basically. Okay, the next slide, I'm going to show you how the fabrication can be done very quickly. Okay, so for example, you can start with a P-type silicon. You can start with an N-type silicon as well. There's no reason why you should always start with a P. All right, then after that, we put an oxide layer. SiO2, silicon dioxide, is actually formed by oxidizing silicon in the oxygen ambient. So the silicon reacts with the oxygen to form SiO2, which is an insulator. Okay, then we put a photoresist. A photoresist is actually a light-sensitive chemical compound. And the purpose of doing so is to allow certain pattern to be transferred onto the P-type silicon. So it looks like this, okay? So you coat it with photoresist. And then on top of that, we place a mask. So the mask is actually containing the pattern that you want to transfer to the P-type silicon. Okay, so the pattern transfer is achieved by exposing the mask to UV light. Okay, so at the area where the photoresist is exposed to UV light, right, the chemical state of the resist will be different from the rest, which are not exposed to the UV light. Okay. All right. So after that, so what happened is that we can then remove the photoresist, and at the same time, okay, the photoresist. Okay, so just now I mentioned that the photoresist which is exposed to the UV light will be chemically changed, so that can be removed, and the photoresist that is not exposed to the UV light will remain. So that kind of serves as a mask, which then allow us to etch away the SiO2 in this region here. And after doing that, we remove the photoresist. So there are a few more steps. They are not shown here essentially. And then after that, we subject the P silicon to arsenic doping or arsenic implantation. All right, as you know, arsenic is a group 5 element, so that will convert the silicon from P to N. Okay, so after the arsenic implantation, you will get an N region from here. And the rest of the steps will be to make the metal contact. And from there, we can actually have a final device shown here. Okay, all right. So this is how the PN junction can be fabricated. It is a vertical device, right? Okay, now you should have this slide. From now onwards, I think you should have all the slides. So there are only 2 additional slides that I didn't include in the earlier slide deck. So the rest of the discussion, I will focus on 3 important concepts. So the first one will be on this thing called the space charge region or the depletion region. The second one is on the built-in electric field. All right, now why built-in electric field is important, all right, we'll see. Now the third one will be on built-in potential. Now notice the word built-in, okay? Now built-in is used to describe the fact that the electric field and the potential naturally exist the moment the PN junction is formed. All right, so this electric field and potential are not as a result of an external applied voltage. Okay. Okay, so let's start to understand how the space charge or the depletion region is formed at the PN junction. To do that, let's examine the electron concentration profile across the PN junction at the very moment it is formed. So the P is on the left and the N is on the right. As you know, electrons are minority carriers in the P region, so the concentration is very low. On the other hand, electrons are the majority carrier concentration in the N region, so its concentration is very high. Okay, so essentially we have a concentration gradient now existing at the PN junction. Okay, so when you have a concentration gradient, what will happen next is that the carriers would diffuse as a result of the concentration gradient. So the electrons in this case would diffuse from the region having a higher concentration towards the region, which is the P side, having a lower concentration of electrons. Okay, so the diagram that you see at the bottom here, right, is the electron concentration profile after diffusion has happened. Right, so the concentration of electron in this part of the N region is now reduced. Okay, and of course the concentration of the concentration of the electrons in this part of the P region is now increased due to the diffusion of electrons from N to P. Okay, so where is the space charge region? The space charge region form is now in the N side. There is another one on the P side, which I will show you very soon. So as a result of the electron diffusion, some electrons have departed from the N region. And due to that, we have a positive space charge region form. Okay, now I want to correct a potential misconception here. Now, the positive space charge region is not due to the holes, all right, that diffuse from the P to the N side, all right, okay? They are the positive charges in the space charge region here. They are not holes that diffuse from the P to the N side. These positive charges are the ionized donor atoms. Remember in part 1, you have studied this doping, and during doping or even after doping, the semiconductor is neutral. Right? If you take the N-type silicon, for example, you add donor impurities, such as phosphorus. So phosphorus will donate its 5th electron to the silicon conduction band, but itself become ionized, itself become positively charged. So the net charge is 0, right? So the phosphorus contributes 1 electron to the conduction band, but itself becomes positive. So the net charge is still 0. But after the electrons have left the N region, diffuse over to the P, then what you have behind would be now the positively charged donor ions, right? So the electron concentration has decreased. So now you have a net positively charged region appearing here, and the positive charges inside this region are the positively charged donor ions. Okay, all right, so remember this. Now, by similar arguments, hole diffusion will happen due to the concentration gradient in the hole concentration, right? So after the holes have departed from the P region, we also have a space charge region form on the left side, which is on the P side, all right? Now, this space charge region contains negative charges, and these negative charges are the ionized acceptor impurity atoms. Okay, so these negative charges are not the electrons that diffuse from the N over to the P. Okay, all right, so take note of that. Now, why do we actually disregard the increase in the electron concentration here, for example, and increase in the hole concentration here after diffusion has happened? The reason why we can do that, as we will discuss later, is that this concentration, this increase in the electron concentration here is actually much lower than the accepted doping concentration on the P side. So in the rest of the analysis, we are going to ignore this increase in the electron concentration. Likewise, we are going to ignore this increase in the hole concentration in this diagram here. Okay, so we're only focused on the ionized acceptor atoms in the space charge region. Okay. All right, so what I've discussed just now is summarized here, so you can read through it later on. Okay. So let me summarize. Okay, so as a result of the concentration gradient in the electron and hole concentration, right, diffusion of electrons and holes will occur the moment the p-n junction is formed. So as a result of this diffusion, we have this space charge region formed, consisting of positive charges on the N side. These positive charges are the ionized donor impurity atoms, and negative charges on the P side, and these negative charges are the ionized acceptor impurity atoms. Okay, so what's next? Built-in electric field. Okay, okay, before that, just to introduce another term to you, depletion region. Now, the space charge region is also called the depletion region. All right, why the word depletion? Because these two regions are depleted of majority carriers. As a result of the diffusion of the majority carrier from one side to the other side, the concentration of majority carriers in this region is reduced, is depleted. So people call the space charge region the depletion region. Okay, so just take note of this term. Okay, so what's next? Right, very obviously, we have positive space charge on the N side and negative space charge on the P side. So what do we have? We have an electric field, all right, that points from the N to the P, like this. Okay, so what does this electric field do? Now, if you look at the electrostatic force that the electric field will exert on the holes and the electrons, right? If you look at the holes, the electric field will exert an electrostatic force on the holes in this direction, in the same direction as the electric field. For the electrons, the electric field will exert an electrostatic force in the opposite direction to the electric field. Okay, so in other words, the built-in field, we call this the built-in field. It forms naturally due to the formation of the p-n junction. The built-in field would serve to retard the diffusion of holes from P to N, as well as the diffusion of electrons from N to P. It serves as an opposing force, right? Trying to push back the diffusing carriers. Okay. All right. So imagine as diffusion happens, the built-in field will exist. As more diffusion happens, the built-in field strength will become higher because you have more space charge now present, right? As more diffusion happens. And then as a result of the built-in field, you will get more opposition coming from the built-in field towards the diffusion. All right. So eventually, all right, the opposing effect posed by the built-in electric field will cancel out the diffusion. And when that happens, the PN junction is said to reach thermal equilibrium. Okay, and the current across the junction will become zero. All right, so that is the purpose of the built-in field. All right, it serves to create an opposing drift current that eventually cancels out the diffusion current at thermal equilibrium, so that the net current flow across the junction is zero at thermal equilibrium. All right. Okay, so take note of the term built-in electric field. I have introduced this term to the 2 tutorial classes that I taught last week. Okay, so you can see it here again because we have an example of a non-uniformly doped semiconductor. Right, a PN junction is a classic example of a non-uniformly doped semiconductor. The doping concentration changes drastically from P to N or from N to P. Okay, so I've mentioned this just now, so you can read it later on. So mathematically, what I can do now is that I can then write down an equation based on what I have just discussed. So under thermal equilibrium, the drift current for electrons arising from the built-in field has to cancel out the diffusion current due to the electrons, making the total equals to zero. Likewise for the holes. Okay, so based on this understanding, and provided we know the electron concentration profile across the junction, so that we can evaluate N and dN over dx, we can then find an expression for the electric field, conceptually speaking. Okay, right? But however, usually we are not able to very precisely obtain an equation that describes how the electron or hole concentration varies across the PN junction. So this equation is only useful conceptually. Later on, I will show you how to go about getting a mathematical expression that will quantify the built-in field across the PN junction. Okay, which is what I'm going to do next. Now, related to the built-in field, you then have a built-in potential. All right, so when there is an electric field, there is always a potential drop across the region where the electric field is. So essentially in this case, all right, we have the N side of the PN junction becoming more positive compared to the P side of the PN junction. Right, so there is a built-in voltage across the PN junction. The purpose of the built-in voltage is the same as the electric field, as the built-in electric field. It serves to oppose the diffusing majority carriers and cancel the diffusion process at thermal equilibrium. Okay. All right, so now what I'm going to do next is to show you how to get a mathematical expression that will quantify the built-in electric field across the PN junction. Now, as I've said earlier, theoretically, it can be done using these two equations. But the difficulty here is that we do not know a precise mathematical form for N, and therefore we cannot evaluate dN dx. Okay. Likewise, for P, we do not know a precise mathematical form. We cannot evaluate dP over dx. So to overcome that, right, what we can do is that we can obtain an expression for the built-in electric field by solving this equation called the Poisson equation. Poisson equation, okay? Now, Poisson equation is a very fundamental equation in electrostatics, and we are now applying it in this p-n junction, okay? So what is the Poisson equation? We only deal with one dimension, right? Because we can think of the p-n junction as a one-dimension device, where the quantity we are interested in varies only along one direction, typically the x direction, okay? So this is the Poisson equation in one dimension, only along the x direction. So the Poisson equation states that the second order derivative of the potential function, right, can be related to the charge density in the region of interest divided by the permittivity of the semiconductor. Now, epsilon r is called the relative permittivity, and epsilon naught is the permittivity of free space. Okay. All right. So this is Poisson equation, which we can apply to find electric field or the built-in electric field. All right. So essentially, you should also realize another fundamental relationship between voltage and electric field. Right. Remember, electric field is minus dV over dx by definition, and therefore I can express d squared v over dx squared, right, as the negative of the first order derivative of the electric field function. So very clearly, if I can solve this Poisson equation, I will be able to obtain a mathematical expression quantifying how the built-in electric field vary across the p-n junction. So I'm going to do next. Okay. Now, before I can do this, we need to understand this term, which is the volume charge density. Okay, volume charge density. Now, in general, we can write rho, the volume charge density, as the sum of four terms like this. Essentially, in a semiconductor, there are four types of charges. All right, the ionized donor impurities, right, denoted by this term QND. Right. Remember, ND is the donor doping concentration. Okay. Now, another type of charge found in the semiconductor, right, is the host, right, which also have positive charges. Now, the remaining two are the electrons and the negatively charged acceptor impurity atoms. Okay, so I can write the volume charge density at any position inside the semiconductor as the sum of these four terms. Okay. Now, since we have assumed uniform doping concentration, so Na and Nd are constants independent of distance. Okay. So they are independent of distance. Now, however, it is important to realize that Na and Nd are in general functions of distance in practical diodes. So I mentioned this point earlier about the linearly graded junction, whereby the concentration profile varies almost linearly across the junction. Okay. But for now, we treat Nd and Na to be constants. Okay. Now, P and N, however, are functions of distance. You cannot assume P and N to be independent of distance. Right, that would not be very realistic at all. Okay. As a result of that, the Poisson equation is very difficult to solve because we do not know how P and N vary across the junction. So it's a similar issue here, right? Now, to overcome this problem, we have to apply this approximation, which we call the depletion approximation. So what is depletion approximation? Essentially, we treat the concentration of mobile charges in the space charge region to be negligible compared to the concentration of the immobile ionic charge. Immobile ionic charge refers to the ionized impurity atoms. Okay, so this is an approximation, right? Again, strictly speaking, in a real practical diode, we do get some electrons and holes present in the space charge region, but we will neglect them in our analysis. Okay. Now, the second assumption we'll make is that the space charge region ends abruptly at two positions, which I call the xn naught on the n side and the minus xp naught on the p side. I don't know whether I have a diagram to show you this. Let me see. Okay, so if you take the metallurgical junction to be the origin, in other words, x equals to 0. All right, so xn naught will refer to this boundary here. Okay, and minus xp naught will refer to this boundary here. So we assume the space charge region ends abruptly at these two boundaries. Okay. Again, this is an assumption because in reality, the space charge region also changes gradually, right, from the space charge region itself into the neutral semiconductor region. Okay, the transition is not abrupt; it's also gradual. Okay. Okay, so with these two assumptions, then we can go ahead to solve the Poisson equation. All right, so I will discuss the solution for the P side at first. Okay, so after applying the depletion approximation, the simplified expression for the volume charge density rho will be like this. So we have neglected the N and the P terms here. Now, if you focus on the P side, there is no donor doping on the P side, so this term disappears. So the volume charge density rho can simply be written now as minus QNA. Okay. Now the minus sign comes from the ionized acceptor impurity atoms. So when you calculate this, the Q here should be a positive quantity. Now, the simplified Poisson equation will now be like this, where on the left you have the first order differential of the electric field function. On the right, you have a constant term, right? Because we have assumed constant doping on the P side. So this equation becomes very easy to solve, right? You just need to integrate this once and you will be able to solve for the electric field function, which is shown on the next slide. Okay, now after integration, you have a constant of integration that you need to find. All right, so this is what I'm going to do next. So C is an integration constant that can be determined by applying an appropriate boundary condition. So what is this boundary condition? Now, there are two possible boundaries for the space charge region on the P side. One boundary is at x equals to 0, the metallurgical junction, and the other boundary is at x equals to minus xp naught. Now, as what I've shown you earlier, the second boundary is between the neutral P region and the space charge region here, this line, this vertical line. Okay, so based on logical argument, we will expect the electric field to disappear once we move from the space charge region into the neutral semiconductor region. So essentially, the electric field must disappear at this boundary, or the electric field must go to 0 at this boundary, right? So we know something about the electric field at this boundary, but we do not know the value of the electric field at the metallurgical junction. So obviously, we need to use this boundary condition when we determine the constant of integration C. Yeah. Okay, right. So we use this boundary condition. So if you put x equals to minus xp naught and then set the electric field to be 0, the constant of integration C can be easily determined. Okay, so after you have done that, then you have fully solved for the electric field function on the P side, which is given by this expression here. Now, what is important to note here is that the electric field varies linearly with distance across the space charge region on the P side. All right, it's quite straightforward to see this is a linear equation in X. Okay, all right, now, at this point, I want to caution you that this result only applies for an abrupt or step junction. Okay, now, if you do not have an abrupt or step junction, for example, if you have a linearly graded junction, this result doesn't apply. Then you have to go back and see why that is the case. If you have a linearly graded junction, the doping concentration term is a function of distance itself. Okay, it's not a constant, but it's a function of distance. If you approximate NA as a linear function of distance, if you try to integrate to solve this first order differential equation, on the right side, you will get a second order function in x. In other words, you will get x squared instead of x. Okay, so the mathematics will be slightly more complicated, right? So to simplify the mathematical derivation, we will assume an abrupt or step junction. So I hope you know the rationale behind this assumption now. Okay, now note that x is negative based on the way we define the x-axis and the origin. So the origin is actually at the metallurgical junction. So positive x actually points towards the n side, and negative x points towards the p side. Okay, all right. Now, since x in terms since x between 0 and x p naught is always bigger than minus x p naught, then the electric field term here is actually a negative term, all right, which is consistent with the direction of the electric field shown earlier here. Okay, so the electric field actually points from right to left or points in the negative x direction. Based on this, we define this electric field as a negative electric field, which is consistent with the mathematics. Okay, negative electric field. All right, okay. So this is the electric field function for the space charge region on the p side. Okay, I think now is the time is 5:10. We can go for a 10-minute break before we continue the discussion. All right, so please join back the online lecture at 5:20. Okay. Now, in the meanwhile, I will still be around. I'll still be online. So if you have any questions to ask, feel free. Okay. Any questions?
I have a question, sir.
Yeah.
Is the concentration gradient is like purposely doped in the semiconductor?
Which concentration gradient are you referring to? Are you referring to the doping or the electron and hole concentration gradient?
The electron, because the last tutorial got the exponential terms, right? So is it like natural one, or you purposely did that?
Oh, I see. For the example we saw in the last tutorial, the exponential term is actually it is a result of doping.
Oh, so it's like we purposely created that there is the electron concentration grade. Electron concentration is like that.
Okay, I won't say we purposely create that. Let me bring you back to this slide that I showed earlier. Remember, I showed you a slide on the fabrication of the PN junction, whereby we can dope a semiconductor region using implantation. Implantation is a process whereby energetic ions are being directed into the semiconductor. So as they enter into the semiconductor, such as the arsenic ions, as they enter into the semiconductor, they will get lodged inside, and then the doping effect will take place. Now, because of the way the doping is done, the arsenic concentration profile is not uniform. All right, it is highest near the surface, and it decreases towards the rest of the P silicon. All right, it decreases as you enter into the P semiconductor region, and we can show that the dopant profile is actually exponential.
Okay, thank you, sir.
Hi, Professor.
Yeah.
May I ask why the electric field is 0 at the edge of the space charge region?
Okay. why the electric field is 0 at the edge of the space charge region. Okay, so let me come back to this. Now, the region here to the left of the space charge region here is a neutral semiconductor region. Okay, where the holes have not diffused across to the end. If you look at the diagrams I showed earlier here. All right, so in this region, the semiconductor is neutral. All right, now in this region, some of the holes have diffused across to the end side. So as a result of that, we have a negative space charge region formed here where an electric field exists. So at the boundary between the neutral semiconductor region and the negative space charge region, the electric field must go to 0. Right? Because when you enter into the neutral semiconductor region, there is no electric field. There is no net charge. Right? The net charge is 0. So the electric field must go to 0 at this boundary between the space charge and the neutral semiconductor region.
Hi, Prof. Sorry.
Yeah.
Sorry, I have one more question. I have a question.
Yeah.
What's this one? We are looking at the P region of the space charged region, right? Meaning the positive.
The P side.
So, yeah, the P side.
Yeah.
So, wouldn't the boundary condition be more apt if we use the boundary between the positive space charged region and the negatively doped region? Since you're assuming that this density is approximately negative Q and A.
Oh, okay. Let me try to understand your question. Your question is that why do we use the boundary?
Yeah, it's like why do we use the boundary between the positively doped region and the negative space charge region when we are actually considering the positive space charge region?
No. Okay. First correction is that the space charge region on the P side, just now the discussion before the break was focused on the P side. So the space charge region on the P side is a negative space charge region. It's not a positive space charge region. Remember?
Oh, okay.
Yeah. And second correction is that a P-type semiconductor, you cannot think of it as a positively doped semiconductor. That can lead to confusion. Okay. Although holes are the majority carriers in the P-type semiconductor, and you know holes are positive charges, but doesn't mean a P-type semiconductor is a positively doped semiconductor. The P-type semiconductor overall is neutral because the positive charges on the holes are compensated by the negative charges on the ionized acceptor impurity atoms. So in other words, this region where hole diffusion does not happen, this region here is neutral. Region here is neutral. Okay? So the net charge is 0, and therefore the net electric field in this region is 0.
Okay, I understand now. Thanks, Prof.
Hi, Professor.
Hi, yeah.
May I ask, just clarify one question? Because you mentioned that we do not know the carrier concentration in the space charge region. Is it because from the previous diagram, like the formation of space charge region, in that diagram, the I think this diagram, it shows that the concentration varies linearly. Is it because it's not actually the case? That's why we don't know.
Oh yeah, you're right. This is a schematic diagram. So when I drew it, I just draw a straight line. But in reality, we do not know how it varies.
Okay.
In fact, it does not vary linearly. Remember, the scale that I indicate here is a log scale. It's a log scale.
Yeah. Oh, okay. Okay, thank you.
Hi, Professor. Can you repeat why is it that we do not need to care about like the region beside the space charge region? Like where Where
You mean
the,
you mean here?
no, like the previous diagram, like
Yeah.
like the
Where?
how to say, where the diffusion like go towards, like to the right, yeah.
To the right here.
Yeah.
Why we do not need to care? We are concerned. It's just that we haven't discussed how the electric field is derived in the space charge region on the N side. We haven't discussed that. We are going to do it after the break. So before the break, the discussion was focused on the space charge region on the P side. Right? We do not disregard this space charge region on the N side. We'll come to that shortly.
Okay. Yeah. Thank you.
Prof.
Yes.
Just to clarify, the electrons that diffuse from the N side to the P side are negligible and they do not contribute to the space charge, the space, right?
Strictly speaking, they do. But the concentration of the electron in this space charge region on the P side is much lower than the concentration of the negatively charged acceptor impurity atoms. So to keep the analysis simple, we neglect the electron concentration here. Strictly speaking, the electron will contribute a negative charge in this space charge region, but we neglected that.
Oh, okay. Thank you.
Sir.
Yeah.
Why there is a region that there is neutral concentration? At the site, why is neutral?
Sorry, at the site.
Yeah.
Are you referring to this?
Yes. Why the set is neutral?
Why is it neutral? Okay. Remember during doping, all right, after you dope a semiconductor p-type by introducing boron, all right, how does boron create the holes in the valence band of, let's say, a silicon semiconductor? It does so by accepting a valence electron, right? So in the process, you have a hole created, which is a positive charge, no doubt. But in the process, the boron atom gains an electron, so it becomes ionized. It carries a negative charge. So overall, there is no net charge because one boron atom creates a hole, but itself becomes negatively charged. So the net charge is still zero. So that's why I say in a p-type semiconductor, the semiconductor is neutral because the holes, the positive charges on the holes are compensated by the negative charges on the acceptor ions.
Okay, thank you. So is it necessarily to be at the site, or we just consider it at the site?
Okay, this question about at the site is due to the fact that the diffusion will always start to happen at the metallurgical junction. All right, and then the space charge region will start to spread towards the rest of the semiconductor region. Right, so this boundary would therefore divide the neutral semiconductor region from the space charge region. So it serves as a boundary where the electric field is known. It is zero. And it is zero because when you move out of the space charge region into this region, which is neutral, there is no electric field. So the electric field must go to zero here at this boundary. So we use this knowledge to find the integration constant when solving the Poisson equation.
Okay, thank you.
Hi, Professor.
Yeah.
May I ask why we need like the concentration of mobile charge in a space charge region are negligible compared to the immobile ionic charge? Is it? I think like, I like this immobile ionic charge are caused by mobile charges moving to the other side.
Oh, yes. Okay, that's a good point. So if you look at electron diffusion, right? So electron diffuse from the N to the P, but the electrons that go to the P will recombine with the holes. Okay. So the concentration will definitely be less significant as compared to the concentration of the dopants in the region.
I see.
Okay. All right.
Okay, thank you.
Hi, Professor. Regarding for this graph, why is the x distance for the space charge region for the n type shorter than the p type in terms of the distance?
Oh,
X.
okay. I think you're referring to the value of xp naught
Yes.
compared to xn naught.
Yeah, yes.
Yeah. Well, this is a random outcome. I just happen to draw it like this. So there is no reason why the width of the space charge region on the P should always be bigger than that in the end. No. In this drawing, I have implicitly assumed that the N side doping is higher than the P side doping. I will come to this point shortly. This is actually referring to space charge neutrality.
Okay. Thank you, Prof.
Professor,
Yeah.
Is the drawing of the negative and positive donor and acceptor just below the axis, just like a way of representation?
Oh yes. That's right. I mean, I just want to show that due to the diffusion of the electrons in this diagram, for example, so the positive donor ions will get exposed. So this region here, where the electrons have diffused across, will become positively charged. So it's a schematic representation. Right. So I think you have asked very good questions. So keep that up, right? Because that will help you understand better. All right. So I think yeah. So now it's 5:28. In fact, the break is already over. So I think we can continue the discussion. Okay. So let me resume the discussion from here. Okay. Yeah. This is where I stopped before the break. So by solving the Poisson equation on the P side, applying the depletion approximation and assuming the depletion region ends abruptly at x equals to minus xp naught, we have come to this result. All right, so please be reminded that this result where the electric field varies linearly with distance only applies in an abrupt or step junction. Now, a similar approach can be applied to derive the equation for the built-in electric field on the N side. So I will leave it as an exercise for you, but I will guide you a bit. So if you go back to look at the Poisson equation at this point, right? We have simplified after applying the depletion approximation. We have simplified the expression for the volume charge density to be like this. So if you consider the N side, the N region, there is no acceptor doping. So you have only the donor doping ND. All right, so rho is approximately QND without the negative sign, and the Poisson equation becomes simplified into this form where the first order derivative of the electric field function is simply equal to QND over the permittivity. All right, so if you integrate and try to find the constant of integration using the boundary condition in a similar way as we did for the P region, then the final result that you get will be here, will be shown here. All right, okay, so similarly, the electric field will vary linearly, all right, across the space charge region on the N side. Now, because N is always smaller than Xn naught, remember Xn naught is the distance of the boundary between the space charge and the neutral N region from the metallurgical junction. So for any distance x from the metallurgical junction within the space charge region on the N side, this value of x will be smaller than Xn naught. So the electric field is also a negative quantity in this case, which is consistent with the direction shown on the diagram. In other words, the electric field points in the negative x direction. Okay. So at this point, right, we have one equation that describes how the built-in field changes with distance in the space charge region on the P side. And we also have a second equation that will describe how the electric field varies with distance for the space charge region on the N side. So the next question that we should answer would be, what about the electric field at the metallurgical junction where x equals to 0? Okay, when you put x equals to 0, the electric field based on this equation would be QND over permittivity times minus Xn naught. But if you do that for this equation, if you put x equals to 0, the electric field will be minus QNA over permittivity times XP naught. They don't seem to be the same. Okay, all right. In other words, can the electric field be different at the same position, metallurgical junction? At the metallurgical junction, can the electric field have two different values? Right. So that is the question that we want to answer next. In fact, the answer is no. All right, because of space charge neutrality. Basically, to begin with, the PN junction is neutral. All right. At the very moment the PN junction is formed, it is neutral. Although after that, interdiffusion of majority carriers across the junction will happen. But even so, due to charge conservation, the space charge region as a whole should still be neutral. So in other words, the amount of negative space charge on the P side must always be equal to the amount of positive space charge on the N side. So this equation here simply states that. So the term on the left gives you the amount of positive space charge on, the amount of negative space charge on the P side, all right, which can be evaluated as the product of the doping density, the acceptor doping density, QNA, multiplied by the volume of the space charge region. The volume of the space charge region can be evaluated by the product of XP naught times A, where you can take A to represent the cross-sectional area of the PN junction. Now, on the right side, we can do the same. We can obtain a term that gives us the amount of positive space charge on the N side by taking the donor doping concentration multiplied by the volume of the space charge region on the N side. So the A and the A will cancel out, giving you this equation. This is called the space charge neutrality equation. Okay, so if you divide both sides by the permittivity, what do you get on the left? You get the electric field at the metallurgical junction evaluated using the expression on the P side. And on the right, you get the electric field, all right, evaluated using the expression for the electric field on the N side at the metallurgical junction. All right, so the two must be equal. Okay, so in other words, the electric field is continuous at x equal to 0. It has only a single value at x equal to 0 because of space charge neutrality consideration. Okay, all right, so with this answer, then we can draw the electric field diagram. Okay, so the electric field diagram will look like this, or the electric field distribution plot. Essentially, it is also called. Simply gives you the variation of the electric field, built-in electric field across the PN junction. So on the P side, the variation is linear. On the N side is linear. Beyond minus XP naught, the electric field is 0. Beyond XN naught, the electric field is 0. And at the metallurgical junction, we have the maximum electric field. All right. Okay. So this is a very simple plot. It's actually a triangular plot. But keep in mind that this plot is only valid for an abrupt or step junction. For a linearly graded junction, the electric field plot will not be a triangular plot like this. Okay, you can go figure out what happens if we have a linearly graded junction. What would be the electric field function across the PN junction? It will no longer be linear, but it will be a second order function of x. In other words, it will be quadratic. Okay, all right. But we will not discuss a linearly graded junction. Okay, so at this point, we have solved the electric field function. It can be quantified using these two expressions, but not quite complete yet because we still do not know the value for XP naught and XN naught. Although we would know QNA and the permittivity term, which is a property of the semiconductor, but we do not know XN naught and XP naught. So we still cannot calculate the value of the electric field across the space charge region, although we have the equation. Okay, so the rest of the discussion will try to find XN naught and XP naught, and in doing so, we can fully solve the electrostatic problem for the PN junction.
Prof.
Yep.
May I ask a question? Is it always for the P side, right? The magnitude of the gradient is always larger than magnitude on the N side, or it depends on the value?
Okay, that's a good point. So are you referring to the slope here?
Yeah.
Okay, so maybe on this diagram, the slope is smaller than the line on the N side, all right? This line has a smaller slope than the line on the N side. No, again, this is due to a random schematic drawing, but it can still be explained. Now, the slope of the electric field plot in the space charge region is related to the doping concentration. You can see that very clearly, okay? So if QNA is high, then the slope will be high. If QND is high, then the slope will be high likewise, okay? Right, so it all depends on the slope. So you cannot just generalize saying that the slope here is always smaller than that on the N side. So you have to look at the two doping concentration. All right.
Okay, I see. Thank you.
Sorry, Prof, may I ask another question?
Yeah, sure.
So for just now the case, does it mean that the value of XP naught and XN naught will depend on the concentration of dopants?
Yes, you're absolutely right. Because of space charge neutrality consideration, if NA is different from ND, let's say NA is much larger than ND, then in order for the space charge balance to be valid, then XP naught must be smaller than XN naught by the same ratio. Okay? Yeah, right.
Okay, thank you.
Okay, so before we leave the discussion on the built-in field, just take note, maximum built-in field occurs at the metallurgical junction. This is always true, regardless of whether you have an abrupt or a linearly graded junction. All right, even if you have a linearly graded junction, although the expression for the built-in field will be more complicated, it is a parabolic function, but the maximum built-in field still occurs at the metallurgical junction. Now you can understand this physically or through a physical argument like this. So let me show you this drawing again. Imagine yourself to be standing at the metallurgical junction, and we do not need to assume that the doping concentration on the N and the P side are uniform. Right? You can make it more general by assuming that the doping concentration on the N side and the P side are functions of distance. Okay, but no matter how, because of space charge balance consideration, if you stand at the metallurgical junction, to the right, you will see the maximum amount of positive charge, and to the left, you'll see the maximum amount of negative charge. So at this position, regardless of how the positive charge and the negative charge vary with distance, at this position, the electric field will always be the maximum. Okay, so that's how you can try to understand why the electric field always is the maximum at the metallurgical junction, regardless of the type of junction. Okay, moving on. So now we still have not completely solved the electrostatic problem, because xn0 and xp0 are still unknown. Okay. So now we want to talk about the built-in potential. All right. So as a result of the built-in electric field, there will be a built-in potential. And in fact, I answered this question earlier during the discussion on the built-in electric field. Which side, N or P, is at a higher potential? Obviously, it is the N side because the positive space charge is on the N side. The positively charged donor ions are always found on the N side. Okay. So now we want to quantify this built-in voltage or built-in electric field. How to do that? We can start by looking at the basic definition for potential and electric field, how the two quantities are related. So the built-in the built-in potential or the built-in voltage can be evaluated by the negative integral of the electric field function. All right, this is a fundamental equation in electrostatic. That's how potential and electric field are related. So if we apply this, essentially we want to integrate the electric field plot, right, to find the area underneath the electric field plot. Right? When you do an integration of a function, you're actually trying to find the area under the curve. All right, so this happened to be a triangle. So it's very easy to find the area of this triangle, right? It's half base times height. So the base length will be xn0 plus xp0, or the total depletion width. And the height of the triangle will simply be the maximum electric field value. Okay, so if we apply this, then we can write VBI, which is the built-in voltage across the PN junction, simply as half times the height of the triangle times the base of the triangle. Okay, so xn0 and xp0 can be rewritten as w0, where w0 represents the total width of the space charge region. Now, even if you do that, however, you still cannot fully solve the problem because w0 is still an unknown, right? xn0, xp0, they themselves are still unknown. So let's see how we can overcome this later on. But at this point, right, you should recall that the maximum electric field at the metallurgical junction can be expressed like this, right? Well, either as QNA xp0 over permittivity, or as QND xn0 over permittivity. The two are equal by space charge balance consideration. So therefore, I can write the built-in voltage, right, either like this or like this. Okay, so the two must be equal, right? Now, so that gives me one equation that relate VBI to xn0 and xp0. Okay, you can choose either one of this to use. Now, we need another equation to find xn0 and xp0 because one equation alone cannot help you solve two unknowns, right? And you cannot use these two equations to solve xn0, xp0, right? Because these two equations are not independent equation. So we need a second independent equation to help us solve xn0 and xp0. And this second independent equation can be obtained from the space charge neutrality equation. All right, this is the space charge neutrality equation coming from here, earlier on, here. Of course, the Q is not a common term. You can drop them, drop both, right, on the left and the right. And what you have left will be just the NA xp0 equals to ND xn0. So this is the simplified form of the space charge neutrality equation. Okay, so two equations in two unknowns, you should be able to find xn0 and xp0. But not really two unknowns. VBI itself is also unknown. So even though you can solve these two equations assuming VBI is known, you still cannot completely determine xn0, xp0 themselves. And wow, nevertheless, let's just try to solve these two equations at first. Okay, so you can eliminate one of the unknown and then you will end up with a quadratic equation which you can solve easily. I will leave that as an exercise for you. So after you do that, all right, these two expression gives you the xn0 and xp0. Right, so xn0 can be obtained as shown here by this expression and xp0 as shown here. Okay, now if you try to evaluate xn0 or xp0, you see that you still can't do it because VBI is not known. Okay, so then we must have another equation that can help us solve VBI. Otherwise, the problem itself remain unsolved. Okay. So how to find VBI will be the focus of the next discussion. Before that, just to obtain an expression for W0, which geometrically can be written as xn0 plus xp0. So you just add up these two expressions here, and after some simplification, you should be able to arrive at this expression. So I strongly encourage you to try that out yourself. Algebraically, it is not difficult. All right, so please try that out yourself. At this point in time, you might also want to check your formula list to see what are the equations that are given. Okay, so as we progress, there will be more and more equations. So you might be overwhelmed by so many equations. So it's good to check the formula list to see what are the equations that are given. So that at least gives you some assurance, right? Okay. Okay, so the focus of the next discussion is on how can we evaluate or calculate VBI, the built-in potential. Now, to do that, we turn to the energy band diagram. Okay, now something which you know already from part 1, all right, but you draw in part 1, you draw the band diagram of either an N or the P separately, right? Now we have a PN junction. So how do we draw the energy band diagram of a PN junction? That will be the question we want to answer. So let's recap what we already know about the energy band diagram. So the diagram you see on the left is for the P-type semiconductor. On the right is for the N-type semiconductor. Now, this is a schematic drawing. So what I'm trying to indicate here is that in the P-type semiconductor, the number of electrons is much smaller than the number of holes. Right. Similarly, in the N-type semiconductor, the number of electrons is much smaller than the number of holes. Okay, so don't take the schematic part too seriously. Right. Okay, so these are the energy band diagram of the N and the P drawn separately. So how do we draw the band diagram for a PN junction? Now, one very important consideration that you must know here is that at thermal equilibrium, the Fermi level must form a single horizontal line across the PN junction. You see, to begin with, obviously the the P and the N, the Fermi level in the P and the Fermi level in the N, they are not at the same level, right? By virtue of the different doping that we have introduced into the two regions. But even though they start off to be at different levels at first, after the PN junction is formed and thermal equilibrium is reached, the two Fermi levels must form a single horizontal line. Okay, so how to understand this or justify this conceptually? I will show you a slide which you should already have as well, this one. Okay, so here I'm trying to conceptually justify why when two differently doped region like the P and N region, when they are brought together at thermal equilibrium, the Fermi level must align. Okay, so you need, sorry, my tuning. What happened to my mouse? The cursor is okay. All right, so it's back. Okay, then, all right, to understand this discussion, you need to recall what you have learned about the Fermi-Dirac function. Okay, remember the Fermi-Dirac function, it should be this diagram. Now, the Fermi-Dirac function gives you the probability of finding an electron at a certain energy level. And this probability is half at the Fermi level, right? If you orientate the Fermi-Dirac graph in this manner, where the vertical axis is now the energy axis and the horizontal axis is the probability axis, right? It gives you a better appreciation of why the two Fermi levels must align at thermal equilibrium, okay? Now, let's recap how the shape of the Fermi-Dirac looks like. Essentially, for energy level above the Fermi level, the probability of finding an electron drops very significantly towards 0. Okay. Now, for energy level below the Fermi level, the probability of finding an electron increases very quickly towards 1. That means it is almost certain that you will find an electron at an energy level below the Fermi level. Okay. So based on this understanding, then we can interpret the Fermi level to be more or less the level that, or the highest energy level that an electron can occupy. This is an assumption. Of course, this is an assumption because there is still a non-zero probability of finding electron at energy level above the Fermi level, but this probability drops very quickly to 0. So as an approximation, I can think of the Fermi level to be the highest energy level that is occupied by an electron. So if you have a material, let's say material A, in this example, so if material A has a Fermi level here, then electrons can fill up all the available energy state up to the Fermi level. And above the Fermi level, all the energy state are mostly empty. Okay, so that is the understanding that we have. Now, if you take another material B, and it so happens that in material B, the Fermi level is below that of material A. So in material B, the Fermi level is here, right? It's lower than that in material A. So they are at different levels at first. So in material B, likewise, the electron will fill up all available states up to the Fermi level. Okay, all right. So now imagine what happened when I bring these two materials in contact to form a junction, which is shown on the next diagram. So when I bring the two materials together in contact to form a junction, there will be a transfer of charges between the two materials. Okay. Now, electrons, in this example, electrons in material A will be transferred to material B. Now, why does this happen? Well, let's go back to this diagram because initially, in material A, we have electrons filled up to higher energy levels than in material B. So when you bring the two materials together, then electrons in material A, which are at higher energy level, they see all the empty energy states in material B. So they easily get transferred over and occupy these empty energy states. All right, so this discussion is made in terms of electrons, but a similar argument can be applied to the holes. So in a p-n junction, when the p and n meet, electrons will be transferred from the n to the p. And earlier on, we said that this transfer is a result of diffusion. All right, so these two explanations taken from two different angles are consistent. All right, so when a p-n junction is formed, all right, electrons will be transferred from the n to the p, right? Similarly, holes will be transferred from the p to the n. So as a result of this charge transfer, the Fermi level will equalize at thermal equilibrium. And only when the Fermi level are equalized at thermal equilibrium, then the charge transfer stops. Now, earlier we argued that the charge transfer stop or the diffusion stop when the drift component becomes large enough to fully compensate it. So it is still consistent. Okay, right? So there's no contradiction between these two explanations, although they are approached from very different angles. Okay, all right. Okay, so a very important conclusion that you need to remember is that for any semiconductor device in thermal equilibrium, the Fermi level must be a single horizontal line with no gradient throughout the entire device. All right, so this applies not only to p-n junction, but it applies to all semiconductor devices. All right, so let's apply this understanding now to the Venn diagram of the p-n junction. So let me go back to the slide for the p-n junction. Okay. Yeah, yeah. Oh, in fact, I've included here, sorry. I think in the updated slide deck, I have included the two slides into the slide deck. Okay, yeah. So I've discussed this too. So now let's draw the Venn diagram of the p-n junction under thermal equilibrium. So as discussed, as a result of charge transfer, and the charge transfer only stops when the Fermi level, when the two Fermi levels are aligned. So in drawing the Venn diagram of the p-n junction, the EF or the Fermi level at thermal equilibrium should be a single horizontal line with no gradient across the entire p-n junction. Okay, so that's the first line to draw. Now, then you can fill in the rest of the details. So on the P side, we have the Fermi level closer to EV. All right, so you should draw EV closer to EF and EC further away. Now on the N side, the EC is closer to EF and EV is further away from EF. So it should be drawn like before, right? Like when you draw the Venn diagram of just a single N-type semiconductor. Now, at the junction itself, then you can join up the lines like this. Okay, so this will be the Venn diagram of a p-n junction under thermal equilibrium. Now, at this point, I just want to point out certain things that will help you understand better. Obviously, by joining up the line like this, and because in the p-type, the EC is further away from EF, and in the N-type, the EC is closer to EF, and based on the fact that the two EFs must align, then the two EC cannot be at the same level like this. Okay, the EC in the P is higher than the EC in the N. Similarly, the EV in the P is higher than the EV in the N. All right, in other words, there is an offset in the Venn diagram across the p-n junction. Okay, all right, so that's the first observation. It's quite straightforward. Now, I think you probably already understood that from the earlier discussion in part 1 that the energy Venn diagram is actually an inverted potential diagram. Why I say that? Because the energy Venn diagram is actually drawn for the potential energy of an electron. So a potential energy of an electron can be written as E equals to minus QV. Since Q is a constant, right, then the energy Venn diagram can also be interpreted as an inverted potential diagram. Okay, so on the vertical axis, when you go up the energy axis, the potential energy axis, you go towards potential energy of 0. right, you also go towards the potential of 0. Okay, all right, vertically. Now, if you move downwards vertically, you go towards more and more negative potential energy for electrons, and therefore you move towards more and more positive potential. Okay, so that's how you can interpret an energy band diagram. You can treat it as an inverted potential diagram, where a very positive potential exists downwards and not upwards. It exists downwards. Okay. Now, based on this understanding, we can therefore say that due to the alignment of the Fermi level, there is an offset in the band diagram between the N and the P side. And this offset is actually consistent with the fact that there is a potential drop across the P and N junction. And this potential is none other than the built-in potential. Okay, and therefore the built-in potential itself can be evaluated simply from the offset in the band diagram. So you can calculate the built-in potential by taking the difference between EC on the P side and the EC on the N side. This difference multiplied by Q, because this potential, this energy band diagram is given in terms of EV. Okay, all right. So you can also evaluate the built-in potential by taking the difference between the EV on the P side and the EV on the N side. They will work out to be the same. Okay, and of course, I can also evaluate the built-in potential simply by taking the initial difference between the two Fermi levels, since it is the alignment of the two Fermi levels that caused the offset in the band diagram. So the built-in potential, QVBI, can also be calculated by equating it to the initial difference in the two Fermi level. Okay, now in part 1, you have already learned how to calculate the position of the Fermi level in the band diagram. And I think now you know why that is important. All right, why it is important to know the position of the Fermi level in the band diagram, because you can use this knowledge to analyze a semiconductor device, such as a PN junction. Okay, so with this understanding, therefore, we can evaluate the built-in voltage like this. I'm just equating this to the initial difference between the two Fermi levels. So let's understand the two terms here. So what is EI minus EF on the P side? So if you go back to this diagram, EI minus EF on the P side is giving you this energy difference. All right, I add this energy difference to the EF minus EI on the N side, which is this energy difference here. So adding these two will give me the initial difference between the two Fermi level. That will give me the built-in voltage itself. Okay, now moving forward, EI minus EF on the P side can be related to the P side doping, remember, through the Maxwell-Boltzmann equation, which you have used earlier in part 1 to find the position of the Fermi level, right? So I can relate the position of the Fermi level to the doping, right? Which is what I'm going to do next. So from the Maxwell-Boltzmann equation, I have the whole concentration given as NV exponential minus EF minus EV over KT. The electron concentration is given as NC exponential minus EC minus EF over KT. All right, I can bring in the term EI into these two equations by doing this. So I will do it only for the P. You can try it for the N yourself. So writing the Maxwell-Boltzmann equation for the whole concentration, in this expression, I have introduced the EI terms, right? I have added minus EI and I included plus EI. So mathematically, I'm not changing this equation. All right, it's still the same as before, because the 2 EI will cancel out anyway. All right, but however, doing so allows me to re-express the exponential term as the product of two exponential functions like this by regrouping the exponent. So in the first exponential function here, I've grouped EI minus EV. So I've taken this term and this term, all right, and use it as the exponent in the first exponential term. Okay. Now, the second one will be here. So I've taken this EF minus EI with a negative sign in front to be the exponent for the second exponential term. Now, by doing that, I can now recognize that NV times the first exponential term is actually equal to the electron concentration inside the intrinsic semiconductor, which is the whole concentration inside the intrinsic semiconductor. Remember, in an intrinsic semiconductor, Ni is Pi. All right, so the product of NV and the first exponential term is actually the whole concentration inside inside an intrinsic semiconductor, which is equal to Ni. Okay, then you just write down the second exponential term like this. All right, so I can express P as Ni exponential Ei minus Ef over Kt. So if you go by the same approach, you can express N as Ni exponential Ef minus Ei over Kt. So if you can do that, then I can find this term and I can find this term. All right, and the whole problem will be solved. Okay, so that's what I'm going to do next. So if you assume complete ionization of dopants in the P and N region, then the whole concentration in the P region can be approximated as Na, assuming Na at the same time to be much bigger than Ni. Similarly, for the N side, I can assume the electron concentration in the N side to be equal to Nd. Okay, so doing so, I can therefore calculate this or evaluate this Ei minus Ef on the P side in terms of the doping concentration. I can do the same for Ef minus Ei on the N side and express it in terms of the doping concentration. The natural log comes from the elimination of the exponential function, right? You take natural log to eliminate the exponential function. Okay, so putting these two terms back into the expression here, I can then arrive at the independent equation for VBI, which is Kt over Q natural log NAND over Ni squared. Okay, so with this, I have fully solved the entire electrostatic problem. Because the doping concentration of the P and N region are usually known, all right, and Ni for a given semiconductor is a material property, it can be known, all right. So at a given temperature, I can therefore evaluate the built-in voltage of a PN junction made on a particular semiconductor of known doping concentrations. So with VBI known, then going back to the earlier equations that you saw, with VBI known, doping known, W0 can be calculated, or Xn0, Xp0 can be calculated, and as well as the electric field can also be calculated. Okay, so Xn0 now is now known. Okay, so you can calculate the electric field on the N side as a function of distance very easily, and as well as on the P side. All right, so as you can see, at this point, we have fully solved the electrostatic problem of the PN junction. So every quantity is now known, the built-in potential, the built-in electric field, and the space charge stored at the PN junction. Okay, all known. All right, so that completes the discussion on the electrostatics of the PN junction. Now, before I finish today, I just want to go through two very simple examples, right? Well, let's see what we can learn from these two simple examples. So in example one, we can calculate the built-in potential barrier or built-in potential of a silicon PN junction, right, at 300K, with the doping on the P side given and the doping on the N side given, right? On the P side is 10 to the power 18 per centimeter cube. On the N side is 10 to the power 15 per centimeter cube. Ni is also known. So it's a simple calculator exercise, all right? But there's something that I will point out later on. Now, if we change the accepted doping from 10 to the power 18, the original value, to 10 to the power 16, what will be the new potential barrier? Okay. So let's do the simple calculation part one first. So just substituting the numbers into the equation and calculating it will give you an answer of 0.754 volts. Okay, so the built-in voltage at a silicon PN junction, in this silicon PN junction, is this value, 0.754 volts. So let's change the doping, right, of the P side from 10 to the power 18 to 10 to the power 16. Well, despite a 2 order of magnitude change in doping, 100 times change in the doping, all right, the built-in potential changes only by 119 millivolts. Okay, all right. In other words, through this calculation exercise, one point that we can learn is that for a given semiconductor such as silicon, the built-in potential is relatively fixed at a certain value about 0.7. No matter how you change the doping concentration, all right, the built-in potential is around 0.7. Okay, so this weak dependence of the built-in potential on the doping stems from the logarithmic function that you saw in the equation here. Okay, all right. Now, at this point, I don't know whether you will ring a bell to some of you. I don't know. Well, after lab 1, I don't know whether this was introduced in lab 1, but any one of you already know something about silicon PN junction, or maybe not, a PN junction diode in general? Or let me ask you this question. What is the turn-on voltage of a diode? Does anyone know this?
Is it 0.7?
Yeah, you probably have been told this, right? 0.7 is the turn-on voltage of the diode. Very good, right? So, what do you see for the built-in voltage value? 0.6, 0.7. Okay, so is there any coincidence here that the turn-on voltage is similar to the built-in voltage by coincidence, or is it, or are the two really related? So that's the next question that we want to answer. All right, that will be the next question that we want to answer. All right, okay, so I will leave that till next week. All right, when we discuss how an externally applied voltage will impact the electrostatic at the PN junction. Okay, so keep that in mind. So let me go through example 2. Okay, so in example 2, you are asked to calculate the width of the space charge region and as well as the maximum electric field at this PN junction where the P side doping is 10 to the power 16 and the N side doping is 10 to the power 15. So let's do the calculation. Now, in the first example, we already have determined the VBI, the built-in voltage at 0.635, right? You just saw this calculation. So to calculate the space charge width, we just apply the equation that we derived earlier. The doping concentration terms are known, VBI is known, the permittivity term is also given. Oh, sorry, it's not given here, but the relative permittivity of silicon is 11.7, all right, and the permittivity of free space is 8.85 times 10 to the power minus 14 farad per centimeter, because I have used the doping terms in centimeter. Right, the doping terms, the value here are expressed in the unit of centimeter. Okay, all right. So after some calculation, you'll see the value for W naught. It is about 0.951 micrometer. So take note of the order of magnitude for the total space charge width. It is on the order of micrometer. It's a very small dimension. It's a very, very small dimension. Okay, right. That's why PN junction and other semiconductor devices can be made very, very small. They need not be very big. In fact, the LED that you use in your lab 1, the size of the LED actually does not reflect the actual size of the PN junction. The PN junction is actually very, very small, micrometer scale. So the size of the LED that you use actually is contributed by the packaging, right, that people have to put together to form the LED, right? Okay, we can also calculate the xn naught value and xp naught. Remember, xn naught is the width of the space charge region on the N side. Xp naught is the width of the space charge region on the P side. And after calculation, you notice that they differ by a factor of 10. All right, in other words, xn naught is much bigger than xp naught. Okay. And why is that so? Wow, space charge neutrality is the reason. Okay, because of charge balance on both sides of the p-n junction, since in this example, the doping concentration of the p side is 10 times higher than that on the n side, okay? So the xp0 is 10 times smaller than xn0, right? In order to maintain space charge neutrality. Or we can say that in a p-n junction where one side is doped more heavily than the other, 10 times or higher than the other side, then the space charge region mostly exists on the lowly doped side of the p-n junction. You can see from this simple calculation, right? xn0 is much bigger than xp0 in this example. Okay, let's calculate the maximum electric field. Right, the maximum electric field occurs at the metallurgical junction. Okay, so the metallurgical junction is x equals to 0. So you can use the equation we derived earlier to obtain an expression for the maximum electric field, which we already did just now. So you can use this in your calculation, or the other one, which is QNA xp0 over the permittivity. All right, after calculating, take note of the magnitude, order of magnitude of the electric field. In this case, is 10 to the power 4. All right, it's 13,400 volts per centimeter. Okay, so you need a large electric field there to block the diffusion of the majority carriers and to cancel out the diffusion of the majority carriers. Okay, so the purpose of these two simple examples is to just let you have a feel of the order of magnitudes of some important parameters related to a p-n junction. And as well as to prepare you this question about, you know, the turn-on voltage of a silicon p-n junction, for example, being 0.7, is there any relation between this value and the built-in voltage value that we have calculated here, right? Which happens to also be around 0.7. Okay, so this question we'll answer next week. All right, so to, by the way, before I leave this discussion on the built-in voltage, let me just remind you that for different semiconductor, although the P and N region can be doped the same as another semiconductor, if you change the semiconductor to a different semiconductor but keeping the doping concentration unchanged, the built-in voltage will change because of the value of Ni, which is different for different semiconductor. All right, okay. So this turn-on voltage of 0.7 only applies to a silicon diode. If you look at a germanium diode, the turn-on voltage will be different. And if you look at the gallium arsenide diode, the turn-on voltage will again be different, right? It is related to the built-in voltage, but how, we will see next week. Okay, to round up, so this is a summary. Okay, so we have solved the electrostatic problem of the p-n junction completely. So we can calculate all the parameters of interest, the built-in electric field at different position, the width of the space charge region, the amount of space charge stored at the p-n junction, the built-in potential, everything. Okay, so that will prepare us for the rest of the analysis. Okay, so that's all for today I have for you. All right, so we still have some time, so you're welcome to stay back and ask questions.
Hi, Professor.
Yeah.
Can you explain again how space charge neutrality? Why there is space charge neutrality?
Okay, space charge neutrality is actually a consideration that arises out of this conservation of charge. Remember, conservation of charge. Well, charges cannot be destroyed or created for no reason, right?
Yes.
So imagine, to begin with, you have the P region, which is entirely neutral, and the N region, which is entirely neutral. So the moment you form the p-n junction, at the very instant when you form the p-n junction, it is neutral, right? So although interdiffusion of the majority carriers have happened to create a space charge region containing net positive charge on the N side and net negative charge on the P side, if you consider the p-n junction as a whole, by conservation of charge, the p-n junction as a whole must still be neutral. The net charge must still be 0. So that's why the positive space charge on the N side must balance the negative space charge on the P side.
Okay, so is this this equation just an approximation, or like, because like if we do not neglect the mobile carrier, like do we need to really account like take into account the charge of mobile carrier?
Oh yes, you're absolutely right. So if you, strictly speaking, of course, if you want to consider the electron and hole concentration, you have to, right? But doing so will not change the conclusion, or even if you neglect, then the conclusion will still remain valid, because the concentration of electrons and holes inside the space charge region or the depletion region are generally much smaller than the respective doping concentration term. So if you go back to the equation here, the space charge balance equation, if you add in the electron and hole terms, right, they are much smaller than this and this term. Okay, so if we neglect them, we do not violate the conservation of charge very significantly. But you are right that this is an approximated form.
Okay.
You're right.
Okay, thank you.
Hi, Professor. Can I ask a question?
Yeah, sure.
So for the same material, a diode, the built-in voltage doesn't differ much according to NA and ND. But what if we reduce NA and ND both to approach zero?
If you reduce NA and ND, yeah, the built-in voltage will, well, of course, it will approach zero, because at the end of the day, if you reduce NA and ND, in the end, you do not have doping, all right?
Yeah.
Both the P and N will revert to becoming intrinsic semiconductor.
Yeah.
So you do not have a junction anymore. So there is no interdiffusion of majority carriers, right? Intrinsic semiconductor, the electron and hole concentration are constant throughout, right? So there's no more junction. So then there is no more space charge region. There is no more built-in field and no more built-in potential, of course.
Oh, so is there a range of concentrations that NA and ND usually take so that the voltage is around 0.7?
Okay, yes, that's a very good question. That is a very practical question. So in practice, we normally do not dope the semiconductor region very weakly. Okay, we normally dope it such that the doping concentration is on the order of 10 to the power 15 to 10 to the power 18. The reason is because if we dope it too lightly or too weakly, okay, then the resistance of the semiconductor is very high.
Oh.
Right? Yeah, so the whole idea about doping is to reduce the resistance of the semiconductor. If you have very high resistance of, I mean, if the semiconductor has a very high resistance, then it is not useful to make to be applied in the circuit, right? Then the voltages that you need will be very high.
Yeah.
So
Okay,
the range of doping is about 10 to the power 15 to 10 to the power 18, right?
Okay.
So
Thank
within
you.
this range, you'll see that VBI doesn't change very significantly.
Yes. I see.
Okay.
I see. Thank you.
Hi, Professor.
Yeah.
Can I ask, I think on slide 32, could you explain the part about it being the energy band diagram being an inverted potential diagram? I didn't really understand that part.
Okay. Let me just remind you. Should I write down or I can just remind you? Remember, there is a fundamental equation relating potential energy to potential. Potential energy E of an electron is equal to minus Q. The minus is because the electron has a negative charge, multiplied by the potential V. Correct? So based on this fundamental equation, and also based on the fact that energy band diagram that we draw, like for example this one, the energy band diagram that we draw is actually drawn in terms of the potential energy of the electron. So the energy level that you see here, like EC, EV, all these energy, so-called energy levels, are referring to the potential energy of the electron if an electron exists at this energy level.
Yeah.
Yes. Then, for any energy level, for any potential energy level in the band diagram, I can convert it into a potential.
Oh, I see.
Right? So,
Yeah.
based on the energy band diagram, if I move downwards, the potential energy gets more and more negative, right? Because you can imagine moving downwards as referring to electrons closer and closer to the nucleus, right? So
Yes.
for electron closer to the nucleus, the potential energy is more and more negative, right? So if you convert this potential energy to a potential, it becomes more and more positive.
Oh, I see.
Right? So on the other hand, if you move upwards, you're moving towards zero potential energy. So if you convert this potential energy to potential, you're moving towards zero potential, denoting a free electron that is not bound to the nucleus, to the positive nucleus.
Oh, okay. I get it. Thank you, Prof.
Hi, Prof.
Yeah.
May I ask, in this diagram, because we want the Fermi level to align, but that will mean that the intrinsic Fermi level will not be aligned.
Yes.
Like in the resulting product. But how is it so? Because I think like the Fermi level is only dependent on the material, but independent on the state, except for the temperature.
Your question is, okay, as a result of the alignment of Fermi level, then the intrinsic Fermi level will not align.
Yes. Why will it change?
Okay. Now I think there is a possible misunderstanding here. Okay. If we talk about Fermi level, like for example, in the p-type semiconductor, if we talk about the Fermi level, this is the Fermi level. The EI does not represent the Fermi level in the p-type semiconductor. There cannot be two Fermi level in a given semiconductor at thermal equilibrium. At thermal equilibrium, there should only be one. So in this p-type semiconductor, this is the Fermi level. The EI that we write here is just a reference denoting the center of the band gap.
Okay.
Right? So this is just the center of the band gap. So this is not the Fermi level. The EI is not the Fermi level, right? This is just referring to the center of the band gap.
So the intrinsic Fermi level of a material may change. It's not fixed.
Okay. The intrinsic Fermi level of a material is always near the center of the semiconductor, near the center of the band gap of the semiconductor.
Yes.
Yeah, it doesn't change. So here is near the center. Here is near the center. Even here, right, where we have the space charge region here, the intrinsic Fermi level is still at the center of the band gap.
Okay. Then now the question becomes how the conduction band energy change.
How the conduction band energy change? Okay.
Yeah, and valence band energy.
Remember earlier on, I answered a question on energy band diagram being an inverted potential diagram. Okay, so you must remember this. Secondly, the change in the EC. So this EC is higher, this EC is lower. This difference is caused by charge transfer.
Yes.
Remember, when the PN junction is formed, electrons and holes are transferred across the junction. So as a result of this charge transfer, one region will become positive, the other region will become negative. So if you interpret this in terms of the energy band diagram, so the the Venn diagram of the two semiconductor cannot be at the same level before, right? Because charge transfer has happened,
Yes.
and as a result of the charge transfer, the N side has a positive space charge region. So that will make the N side more positive with respect to the P. And therefore, the Venn diagram on the N side will shift down relative to the P. Remember, the Venn diagram is an inverted potential diagram. If you move downwards, you are going towards more positive potential.
Okay.
So this relative shift is reflective of the fact that there is a voltage difference across the two regions due to the charge transfer.
Okay.
Right?
Okay, thank you.
Hi, Professor.
Yeah.
Can I ask about the because the there's this part that is related to the intrinsic electron concentration. So does it matter if, let's say, the P side is a different material than the N side?
You mean the P side is a different semiconductor?
Yeah, so like let's say you combine silicon and germanium.
Okay. So your question is it possible?
Yeah, and if so, what's the result?
Oh, okay, that's a very good question. So it is possible, yes, it is possible to combine a silicon and a germanium to form a PN junction. Now, if you do that, then other considerations have to come in because the two materials have different band gap. Right, so silicon has a larger band gap than germanium. Then if you do that, then there is a band misalignment at the metallurgical junction, right? The band gap is different. So because of this, the electric field would be discontinuous at the metallurgical junction. There is a electric field discontinuity present at the metallurgical junction. We will not discuss this, but essentially you can still understand the basic operation of heterojunction. By the way, yeah, PN junction formed using different semiconductor is called a heterojunction, right? So you can still understand the behavior of a PN junction of a hetero PN junction in the same way as a homo PN junction. Except that there are certain things that we need to consider now because of the two different materials. One of which is the discontinuity of the electric field at the metallurgical junction. But this doesn't affect very significantly how the PN junction perform.
Okay, thank you.
Hi, Prof. Can I confirm a point?
Oh, yeah, sure. No problem.
Okay, so for the built-in electric field, right, it's always negative. It's just that the magnitude changes, right?
Yes.
Oh, okay.
Hang on. For the way we orientate the PN junction, remember I told you we put the P on the left and the N on the right? So the P region is actually in the negative x-axis region, and the N region is in the positive x-axis region. And because in the PN junction, the positive space charge is always on the N side, then the electric field will always point from N to P. The built-in field will always point from the space charge region in the N to the space charge region in the P. So by this convention where the positive x-axis point to the right, the electric field is negative. Now, on the other hand, if you put the N on the left and the P on the right, nothing stops us from doing that. if you do that, then the electric field, since it always points from N to P, then if you change the orientation of the P and N, then the electric field will become positive.
Okay, I see. Thank you.
So the point is that the positive or negative electric field simply denotes the direction of the electric field, right? Other than that, of course, the magnitude is another important value that you need to take note of. Okay, any other questions?
Hi, Prof. Maybe a question not really relating to the what was taught in this lecture, but on the timetable, it says we have a test on the 23rd of March. May I know what are the topics tested for this test?
This is the first test, test 1. So the scope will be for part 1. This test is for part 1.
So from lectures 1 to 8, is it?
No, lectures 1 to 7.
Oh, okay, can. Thank you.
Until non-equilibrium. Yeah.
All right, thank you, Prof.
Oh, hi, Prof. Building on from that, I think at the start, they said that they'll give some sample, like past year papers. Will they be releasing that on the platform?
I believe so. For part 1, Prof. Ng will release some practice question. In fact, I have already done that for part 2. Right, there's a practice question set. So in this practice question set, the questions are actually from past year exams or past year tests.
Okay.
Right, so you may send him a request to see if he can post that as soon as possible.
Okay, thank you.
By the way, just to add on that, for the tutorial 1 to tutorial 6, the last 1 or 2 questions in each tutorial, they actually are from past year tests or past year exam questions. Right, they may not be in the form of a complete exam question, because a complete exam question is possible only when all the topics have been taught. So those tutorial questions that you see in tutorial 1 to 6, the last one especially, could be part of part of a fuller exam question. So you should have a good feel of the standard of the test or the exam question.
Thank you.
Right. Okay. Any other questions? Okay, if you have no other questions, now you can sign off. We can close the session for today. Now, if you have a question later on, you can always send me an email anytime, right? Feel free. No restrictions. Okay? All right, so hope to see you next week, same time. Right, for the lecture 9, during which I will discuss the effect of external voltage on the PN junction in electrostatics. Okay, see you guys and have a good weekend, right? The weekend is coming up soon, right? So have a good week ahead and see you next week. Okay, bye-bye.